After he died in 1727, Sir Isaac continued to be a towering figure in the 18th century. In every field of endeavour, people wanted to be the Newton of their subject. Adam Smith wanted to be the Newton of economics. Some called William Cullen the Newton of medicine. Jeremy Bentham strove to be a Newton of social and political reform. As the poet Alexander Pope joked, nature and nature's law lay hid in night. God said, "Let Newton be," and all was light. Let's look at three examples: the causes of the tides, the shape of the earth, and the number and orbits of the planets in the solar system. Aristotle had drawn a connection between the tides and the moon. For Newton, gravity was the key. He argued that the moon's gravitational pull is greatest when the moon is closest to the earth. Newton was right to think that the tides illustrated gravity in action. Later Newtonians refined the master's calculations. The Swiss doctor Daniel Bernoulli offered a closer analysis of tides in 1740. His work on tides was in response to a question set by the Academy of Sciences in Paris, which offered a prize for the best answer. Learned societies often did this. Bernoulli shared the prize with several others, each helping to explain why tides behave as they do, and including in their explanations the effect of the gravitational pull of the sun as well. The Paris Academy of Sciences was also involved with a second major question of Newtonianism. Was the Earth a round ball? Newton had said no, since he had shown that the force of gravity at the equator was slightly different from the force of gravity in the northern Europe. He knew this by experiments with a pendulum. The swing of a pendulum is influenced by the force of the Earth's gravity. The stronger the gravity, the faster the pendulum moves, and so it takes a shorter amount of time for it to complete its to and fro cycle. Sailors had measured how far the pendulum swung in exactly 1 second. Consequently, Newton said that the Earth was actually flattened at the poles, as if it had been squared from top to bottom, and it bulged a bit at the equator. When Newton's work was being debated in France during the 1730s, many French scientists refused to believe that the Earth had this imperfect shape. So Louis XV, King of France, sent out two expeditions, one to Lapland near the Arctic Circle and one to Peru near the equator, an expensive way to test a simple fact. What the two expeditions did was to measure the precise length of 1 degree of latitude at these two locations. The Lapland expedition returned first, but when the Peru group came back after 9 years, it was shown that the degree of latitude in Lapland was longer than the one in Peru, exactly as predicted by Newton's model. These results helped raise Newton's reputation in continental Europe. Astronomers all over Europe were looking at the stars and planets in an attempt to predict how they moved. One of the most important of these stargazers was a refugee to England from Germany, William Herschel. One night in 1781 he noticed a new object which was not a star. At first he thought it was probably a comet and he described it to a local group in Bath where he lived. His observation attracted the attention of others and it quickly became clear that Herschel had discovered a new planet. It was eventually named Uranus after a character in Greek mythology. The discovery changed Herschel's life and enabled him to devote himself entirely to astronomy. In all his work, Herschel was helped by his sister Caroline. He realized that our galaxy, the Milky Way, was not the only galaxy in the universe, and he puzzled long and hard about what were called nebulae, areas in the sky that appeared as fuzzy white blotches. Herschel showed that some of them probably are, but the others were enormous areas of gaseous clouds swirling around in deep space. Newton's gravity was shown to extend even into the outer reaches of space. Newton's law of gravity and of motion, along with his mathematical analysis of force, acceleration, and inertia, became the guiding principles for natural philosophers during the 18th century. No one did more to show how much these principles could explain than the Frenchman Pierre-Simon de Laplace. Laplace used Newton's law of motion and his mathematical tools to show that the things one could see in the sky could be understood and the future movements of planets, stars, comets, and asteroids could be predicted with accuracy. He developed a theory of how our solar system with the sun and its planets could have been born millions of years ago from a vast explosion. He called this the Nebular Hypothesis. Laplace was describing a version of what we now call the Big Bang. Laplace was so impressed with the power of Newton's laws of motion that he believed that if we could only know where every particle in the universe was at a given moment, we could predict the running of the whole universe to the ends of time. What he meant was that the laws of matter and motion were such that the whole universe really did work like a very well made clock, and that it kept perfect time. His vision of a clockwork universe served scientists for a century after him. That was it. See you next time.